what we are going to do today is, firstly, I'll walk you through some of the important aspects that we have left behind in lecture number three, which is projection, orthonormal matrices, orthonormal vectors, and so on. And then we'll first figure out what exactly is Gram-Schmidt process or GS process of orthogonalization, right? So these are concepts which are derived from uh, the intuition of them is derived from basically how do you get to orthogonal vectors given a set of vectors, how do you orthogonalize them, right? So I will look into or we will understand them from projection point of view. How does projection helps us to uh, basically make the set of vectors which are not perpendicular, is there a process that we can make them perpendicular? That's all. Okay, and we'll learn about it. So let's look into it. Let's go into the details of that. Okay. Now, if you look into your lecture number three, this is obviously your one of the important lectures that you have, and uh, in this entire assembly of lectures, both from your exam point of view, also from the intuition point of view. Okay. Now we have already gone into dot products, then we looked into inner products. What is happening? Just a minute. And let me unmute all of you for some time and then, sorry, mute you all for some time and then I'll unmute you. Okay. So the first thing that we're going to get started with is first today, after going through inner products, dot products, Cauchy Schwarz inequality, you have looked into the cause of in the two vectors and cosine similarity and so on. We discussed only the basics of what exactly lies within dot products, why it is important. But one other important aspect of dot products is basically projection. And projection is what you are going to learn today. We'll first learn about what exactly is projection, how it is used, in what context it is used, why important in machine learning. Okay. And then we will get into why projection is, how projection is linked to your QR decomposition or matrix decomposition. Within that, you have QR decomposition, right? So in your assignment, you have LU decomposition, one question on LU decomposition, one question on Cholesky, and one on QR, I believe, right? So this is what you already know. It is just that you will be discovering what exactly Cholesky and LU decompositions are. You might have not figured out what exactly they are, but I'm telling you, you already know about it. Okay, so and we have already gone through it in the previous lectures, so you'll understand what exactly they are. But QR decomposition, because we were looking into dot products and all, we will first start with projection and then how projections are used in QR decomposition and so on. So this is the idea for the first half. For the very first 1 hour of time, we'll discuss about it. Second hour, we'll get started with second important topic is on determinants. We will first understand what exactly are determinants, how are they used, because determinants are very well used in while computing eigenvectors and eigenvalues. And your next lecture is on eigenvectors and eigenvalues. Lecture number 4 is entirely on matrix decomposition or let's say finding out the eigenvectors and eigenvalues of your matrices. Yes, and eigenvalues. So to find eigenvalues, you first need to know how do you find eigenvalues using determinants. There is slight dependence on determinants. That's why we are studying determinants first, and then we'll look into how do you find out eigenvectors and eigenvalues of a matrix using determinants. Or actually, uh, it's a very simple usage of that while finding eigenvalues. And then that would be it. So the rest half, I don't believe we'll be able to complete the fourth lecture. If you look into in your fourth lecture, you have these are all determined eigenvalues and so on. But later on, you will see in your lecture number 4 slides, and this is already there on your LMS or eLearn portal. So I might not have added it, but you already have the companion doc for lecture 4. So you'll understand that spectral theorem and all, which is included here. This is what we'll not be able to complete. If somehow we are able to get into this, I'll just give you an intuition. But my belief is we'll not be able to get to spectral theorem. So with that, let's get started on projection first. Okay. Now, when we hear about projection, let's say that we have 2D plane. We have two different axes, X and Y. Let's say we have two different vectors. A vector is V here, and there is a vector U. Okay. When I say projection, projection means what part of V, this particular vector where my cursor is, what part of V lies in the direction of U. So when I say I want to project vector V onto U, you might find something like this, projecting that vector onto U. Now the part, if you think of it, this particular part, which basically lies in the direction of the vector V's part, which lies in the direction of U, is what projection is. Projection is always thought from the perspective of perpendicular direction from that vector to wherever you are projecting. So you will hear this concept projection not only right now in terms of finding how much aligned two different vectors are, or finding how different types of things are aligned when you take many different vectors. But you will also see that this projection is what you will look into when you will be projecting the entire data set from ML point of view. Let's say when your data resides in lower dimension and you would want to project the data into higher dimension, you will hear these terms. So the concept, the intuition of projection comes in from here. Okay, you will understand when we say we are projecting data points from, let's say, uh, one particular space to another space. The entire concept that you will be hearing, they are all made up of what you are going to hear in next 20, 15, 20 minutes. Okay. So projections are always thought from the perspective of perpendicular angles from the tip of the first vector to the direction of the second vector. Okay. Why do we say it's always perpendicular? Why are we only looking into the direction? Why we are only looking for perpendicular angle from the tip of first vector to the direction of the second vector? Think of it as when we project a vector on another vector, we are essentially asking this geometric question: what is the best possible approximation of vector view V in this particular case using the direction of U, right? And when we say approximation, approximation always has an error, right? And in vector math, the error is the third vector. This is the difference between your original vector, which is the V vector, and your new approximation. This is the approximation. Let's call it as approximation. Okay. Now, this approximation would be best only when if you think of this length, that is dotted length, is smallest, right? Now, the dotted length is only smallest when it is a perpendicular. You already know that the distance between a point to a line, it's smallest when it is perpendicular. Think of it as, if I consider this distance, it would be longer. If I consider this distance, it would be longer, right? So the smallest possible approximation error that I can get is when I project it perpendicularly. Okay. Now having this in thought, let's say, let me redraw it because I have made it very cluttered. So what we are saying, essentially saying in projection is, when we have two vectors, let's say this is v vector, this is u vector, how much v vector is aligned in the direction of u vector from the perpendicular point of view, okay? From when we are approximating v in the direction of u, how much of v is actually aligned in the direction of u? That's what is a projection. But when we say direction of u, think of it as, when I say direction of u, so the part of v vector which is aligned in the direction of u, it has to be of this form, alpha times u, isn't it? Any vector which is aligned in a direction of u vector has to be of the form alpha times u. This right? This is right, right? Yes. No. Right. So so direction of u means alpha times u, right? Now let's say that we want alpha times u. Let's say this entire thing that you have projected, this is alpha times u. Okay. What we want, what we want is, we want v minus alpha u. Let's say the vector v, which is the original vector we are projecting, and we are projecting on the direction of u. Vector v minus alpha times u has to be, this entire thing has to be perpendicular to u vector. That's what we are looking into. This is what v minus alpha times u is. This has to be perpendicular to the u vector, right? When two vectors are perpendicular, then we can also write it like v minus alpha times u dot u is equals to 0. You already know that when two vectors are perpendicular, they are, and their dot product is 0, right? Because cosine similarly, because you have cos of 90 degrees, cos 90 is equals to 0, right? So you can write it like this. Now, or else you can also write it like u transpose, another way, u transpose v minus alpha u is equals to 0. Now, when we look into, and both of them are the same form, right? You can write dot products as v dot u, or you can write dot products as u transpose v, or v transpose u, right? Or let's say u dot v dot u. This is one way of writing it. Other way of writing it is u transpose v and v transpose u. So when I write it in this form, if you think of, I can also write it like v dot u minus alpha u dot u is equals to 0, right? Or else I can write it like alpha is equals to u dot v divided by u dot u, right? So that's what it is. Now we wanted to get alpha u. So in that case, alpha u would be basically the projection of the first vector v in the direction of u. That was alpha u. So alpha u in that case would become u dot v divided by u dot u into u, right? So that's what it is. Now think of it. This is a scalar number. This would be a scalar. Okay. So what you're saying is the projection of v vector in the direction of u is alpha u, and that formula is u, sorry, this is u dot v, not u dot u. U dot v divided by u dot u into the vector itself, right? So this is a scalar number into alpha u, right? So now you can also write it in the other form when you expand the second equation, which is u transpose v minus alpha u transpose u is equals to 0. And you can write it as alpha is equals to U transpose V by U transpose U, or you can write alpha U is equals to U transpose V by U transpose U into U, right? So that's what it is. Now, this is simple. You can write projection as this, or you can write projection as this. Both the formulas are same. It's just that the intuition is how much aligned V vector is in the direction of U. So that's what you have it here. If you look at it from dot product, right? If you see here, this is what projection is. You have V vector, you have U vector. What we're looking into is how much of V is aligned in the direction of U. When I change these vectors, the alignment would also change, right? That's what you're looking into. This is the projection that you see, the projection word that is written there. That's the projected vector. See here, projection of V onto U. It's calculated, and that is a vector because we want to see how much proportion of V is aligned in the direction of U. See that pink line, it is always perpendicular, no matter wherever you go to. Now, when the vectors are actually perpendicular, U and V are perpendicular, okay. In that case, almost, let's say, the projection of V onto U would be almost zero, and that's what you are seeing here. Okay. And this is the concept that you will realize next when we go deeper into it. But this concept is fairly simple, right? Projection is nothing but using the dot products, we are just trying to find out how much of a vector V, or let's say any other vector, is in the direction of the second vector, or how much of first vector is aligned in the direction of the second vector. That's all we are trying to find out. Okay, good. The projection would be zero only when you have the vectors which are perpendicular. Okay, that's the only case. And the second question which was there, is that whiteboard. So if you think of it, we want vector V to be projected on the direction of U. So where that projected vector would lie, let's say this is V vector, this is U vector. We want the second vector to lie somewhere U. So we want how much of V is aligned in the direction of U, right? Now, in the direction of U, the best possible approximation of U is only when the first vectors, let's say, this distance is minimal. This distance is minimal only when we have the line, or this distance line is perpendicular to the second vector, which is U vector. Now, that's what we are saying. Let's say, if you think of it as we have V vector, okay, and we want V minus alpha U because this is the projected vector and this is the original vector. We want this particular part, V minus alpha U. This is V minus alpha times U. We want this particular part perpendicular to U vector. The reason for that is we want the best approximation possible by projecting the vector. Okay, that's why V minus alpha U has to be perpendicular to U. So this is the length, that dotted length that you see here is V minus alpha U. Why V minus alpha U? Because this is V vector, and how much amount of that vector is aligned in the direction of U is alpha U. If you subtract both of them, basically this is what you'll be getting. Okay. Now you know that when you subtract a vector, now this is the concept that you should be learning. The concept is when you project a vector on the direction of another vector, okay, let's say that this is the projection. Okay. When you take difference of the original vector minus the projection of the vector in the direction of U vector, okay, then you will find that this entire thing is always perpendicular to the second vector that you have. And this is the intuition that you should be getting to, because the next part that we are going to learn is all dependent on this. Okay. Now the next thing is Now the next thing is let's not discuss Graham's commit because we will if we discuss Graham's commit in terms of what it gives you, you may be lost. So let's take three different vectors. Let's say that, and let's think of three different vectors which are dependent so that you understand the entire essence of Graham's commit. Okay. Let's say three different vectors which are there 1, 1, 0. This is vector 1. Let's say vector 2, which is 2, 0, 1. And let's say there is a third vector which is 3, 1, and 1. Now, are these vectors linearly independent? Are these vectors linearly independent? Yes, no. I'll give you a minute. Let's say that. These vectors, are they independent or not? Are they linearly independent or not? No, no, right? Because V3 is equals to, essentially speaking, V3 is equals to V1 plus V2. That's right. That's right. Now, because V3 is equals to V1 plus V2, these are dependent vectors. These three vectors are dependent. You can say that V1 and V2 are independent, but at least V3 is dependent on V1 and V2, and hence the set of vectors are dependent vectors. Now, what GS does, or Gram commit, the process GS does is, and you have essential visualization of GS here, Gram commit. So we'll get into that. But let me first help you understand what is the intuition for Gram commit. Let's say that we have three different vectors, not essentially all of them perpendicular. What Graham's commit does is it carves out the independent directions, the independent vectors out of these three vectors. So let's say that let me plot it on two dimension. Let's say that we have two different vectors, this vector and this vector. Okay. Now what Graham estimate does is it basically takes out what portion of vector, let's say this is vector v, this is vector u, what portion of vector v is not aligned in the direction of u, which is basically the perpendicular direction. Think of it as this one. Okay. Now if I shift this particular vector, the dashed vector from origin, it would look like this, right? Now if you think of it as this is perpendicular to u vector, now this is the entire thing which Graham's commit does. Graham's commit, what it does is it tries to find out of how much of V is not at all inclined in the direction of U. So basically it tries to find out two vector, given the set of vectors, it tries to carve out the non-dependent part of the two vectors. Now think of it in machine learning terms. If you have a set of users and you apply Graham's commit on those set of users, it would essentially find out what are unique set of users which exist in your data, because it just eliminates the part which is alignment, right? So if you see here, the alignment part, which is this one, this length, it has been subtracted from v vector, and that's what we when we did v minus alpha u, we found this particular vector, right, which is here, this one. So we just shifted this vector from origin, that's all. And what we found out was this particular vector v minus alpha times u is perpendicular to u, right? And hence these two, this particular vector and this vector, they became independent. Now you also can say that Graham estimate helps you find out independent directions or independent vectors from a given set of vectors. Now this is what we will be learning by applying Graham estimate to these three vectors. So let's get started. So what the very first step is, remember these three vectors. The first step is you transform the very first vector v1 and you say that u1 is equals to V1. Just not transformation, you're just renaming it as U1 is equals to V1 just for the sake of projection so that you don't get lost into V1, V2, and V3. Okay, so U1 is equals to V1, which is essentially speaking is 1, 1, 0, right? Now, we in step number 2, we would want to remove overlap of V2 along U1. How do you remove overlap of V2 along U1? So let's say this is the first vector. This is the first vector V1. We have just termed it as U1, right? And the second vector is V2 is 201. You just have learned how do you remove the overlap? How do you remove the overlap of V2 along U1? To remove the overlap, the very first thing that you'll have to do is you'll have to find how much of V2 is aligned in the direction of U1, right? So basically projecting V2 in the direction of U1, that's what you'll have to first find out. So that would be, you already know that formula, V2 transpose U1 divided by U1 transpose U1 into U1, right? That's what we are doing. You were just using the same formula of projection that we carved out this entire thing, right? You're using that formula to project V2 into the direction of U1. So this is that formula. And what would that be? So let's say V2 is 201, U1 is 110. What would be the dot product between them? What would be the numerator part? The dot product between U1 and V2. What is the dot product between this vector and this vector? And basically the numerator part. 2, 2, right? Essentially. So if you see here 2 into 1, 0 into 1, 0 into 1, it would be 2. What would be the denominator part? The dot product of U1 with itself. So how did we land to 2? It's basically 2 times of 0 plus 0 times of 1 plus 1 times of 0. That's how you got to 2. And the denominator is essentially, if you think of this particular part, this is what this is. The denominator is U transpose U. What is the denominator? Denominator would be U1 transpose U1. The dot product of U1 with respect to itself. What would be that? 2, right? Exactly. Because it is basically saying 1.1 plus 1.1 plus 0.0. So it would basically 2. That's what you have. So you got 2 by 2 and U1 vector. U1 vector is what? 1, 1, 0. That's what is U1 vector. So basically you have got projection of V2 onto U1 is nothing but this vector, which is 1, 1, 0. Okay. Now you have got 1, 1, 0, which basically is the projection. But if you have to remove the overlap, you will have to do this. You will then name a new vector U2, and you will say that U2 is equals to V2 minus projection of V2 in the direction of U1. So you will have to remove the overlap part, right? How much of V2 is aligned in the direction of U1? If you remove that part from V2, you basically are going to get the perpendicular direction, right? So basically you will be getting what is your V2? 201, 201 minus projection of V2 into direction of U1 is 110. So basically you are getting 1 minus 1, 1. Right. So this is the vector that you got. Now, just to verify, cross verify, are they perpendicular or not? You can simply do U1 dot U2. So U1 vector was 110, 110, and U2 vector is 1 minus 1, 1. When you do a dot product, what it would be? 1.1 plus minus 1.1 plus 0.1, right? Which is basically 1 minus 1 is equals to 0. So basically now the second vector that you have carved out by removing the alignment of V2 in the direction of U1 from V2 itself, you have found out that both of them have become perpendicular. Okay. Now the new vector, basically what you're saying is the new vector that you have got is perpendicular to the direction of the first vector. Okay. Now If we have to remove, let's say that if we have to remove overlap of, let's say, overlap of V3 with V1 and V2. Let's say we have to remove the overlap of V3 from V1 and V2. What we'll be doing? First, we will re change V3 to U3. Okay, and then we'll say that U3 is equals to how much amount of V3 is basically aligned in the direction of projection of V3 in the direction of U1, because that's a first vector, minus projection of V3 in the direction of U2. So now you will be getting U3, which would be perpendicular to both of these previous directions, U1 and U2. Now this is the same thing that you will visualize here. Let's say, because I could not draw 3D, I'll just show it to you in two vectors. Let's say you have got two set of vectors, V1 and V2. The simplest thing is, first you project the vector in the direction of the second vector. That's a projection. You take a difference. Now you see E1 and E2, they are all both perpendicular to each other. Simply speaking, what you essentially did. So if you think of, you first took the projection, then took it from origin, or basically just to show, just to visualize, we are showing you E1 and E2, which are perpendicular to each other. But if you look from this point of view, let's say that this is the first part, right? You first took the projection of V in the direction of U. You have got this. As soon as you subtract V from this projection, you basically get this green vector, right? This is what is perpendicular to you. Now, because it is perpendicular to you, I'm just for the sake of visualization, I'm just shifting it to origin because it becomes much easier to visualize. And that's when you will see that this is shifted to origin. Now, both of these vectors are perpendicular to each other. Now, what you can do is you can just take a normalization of them. Dividing the vector by their length is called as normalization. Now, what we are doing is we are just transforming them to unit length. When you divide a vector by its own length, you will see that the vector's length would be always one. Okay, and that's what you're seeing here. This particular vector is of unit length. It all lies in the unit circle. This particular vector is also of unit length. Now, that's what you're seeing. This is the normalization part. But essentially speaking, what you're doing, you started with three different vectors. Okay, and you just said that you had 110, 201, and 311. Now the first, you already knew that the third vector, and this is what we'll get to in a bit. You said you already know that third vector is a linear combination of first and second vector. So what we started with is we just rename first vector just for the sake of projecting and finding out the new vectors. Let's say U1 is equals to V1. Okay. Now we want to remove the overlap of V2, the second vectors, in the direction of U1. So we'll first project it in the direction of U1. You will use the projection formula. We found that the projected vector is this 110. Hence the difference, the second vector that we will have to find out, U2 would be V2 minus the projection. And that's what we found out. Once we found out, we just took a look into how they are. Why are we saying that they are actually perpendicular? We took a dot product and we found that the dot product is zero, right? Because the dot product is zero, we know that they are perpendicular to each other. Now, if we have to remove the overlap of V3 with V1 and V2, you just have to rename V3 with U3, and you will say that you will remove V3's overlap in the direction of U1 and V3's overlap in the direction of U2. Now, just to help you do that part, let's say that let's do it. Let's do the very first part. So herein the formula would become V3 dot U1 divided by U1 dot U1 into U1 minus this particular part would become V3 dot u2 divided by u2 dot u2 into u2, right? And then v3 minus this. Now v3 dot u1 is, if you look into the vector, let me write the vector here so that it becomes convenient for us. V3 vector is 3 1 1. Okay. And u2 vector is what you had, the first vector, 1 1 0. This is v3. This is u1 1 1 0. And u2 vector is what you got as 1 minus 1 1. 1 minus 1 and 1. Now these are the three vectors. Let's take the dot product. So let's take the projection. v3 dot u1, you have these two vectors, 3 into 1 plus 1 into 1 plus 1 into 0. So it would be basically 4 at the top, divided by u1 dot u1. You already know it's 2, right? Into u1 minus this particular part v3 dot u2, 3 into 1 minus 1 into 1 plus 1 into 1. It basically would be 3, right? 3. And u2 dot u2, you should cross verify. I don't know what it is because I'm doing it live. So and this particular part u2 dot u2, the denominator part u2 dot u2 would be 1 dot 1 minus 1 dot 1, 1 dot 1. It should be 3, right? Into u2. Now basically what you are getting is v3 minus 4 by 2, or basically v3 minus 2 times of u1 minus u2. Now if you rewrite the vectors, v3 was 3 1 1, 3 1 1 minus 2 times of u1, which is 1 1 0, 1 1 0, minus u2 vector, which is 1 minus 1 minus 1 1. Now if you look into it, this would become 3 minus 2 minus 1. It is basically 0. 1 minus 2 plus 1. So basically 1 plus 1, 2 minus 2, 0. 1 minus 0 minus 1 is 0. So what are you getting? You're getting u3 is equals to, basically this is what u3 is, right? u3 is equals to this. So u3, you are getting it as 0 0 0. And you already knew that the third vector is already dependent. So there is no part of u3 which is aligned. Every part of u3 is aligned in the direction of u1 and u2. That's why you see that there is no new information that is coming out of u3, right? So think of it as, what does this basically means? After removing previously explained directions, in this particular case, after removing previously explained, or whatever v3 is explained in terms of u1's direction, in terms of u2's direction, there is nothing new in the third vector. That's what you have got. And because there is nothing new in the third vector, what would be the rank in this case? What is the rank? Rank is 2, not 0. The total number of unique information that you have, right? So you have got 2 unique vectors out of 3 vectors. Hence, rank is 2. What is the basis? What would be the basis? Basis would be constituted of which particular vectors? U3 is 0 vectors, that's right. V1 and V2, exactly. So V1 and V2 would constitute your basis. Or basically the transform vector U1 and U2 would constitute your basis. Now, why rank 2? If you think of, rank is equals to, you already knew that the rank is 2 here in this particular case, when as soon as we started, because there are only 2 independent vectors, the third one is dependent on them. You already knew that rank is 2. But when you have too many vectors, you will not know, right? So gram estimate, what it does is, it helps you find out what are the unique directions in our data, what are the unique vectors in our data. Think of, you have millions of data points, millions of vectors of Netflix users. Now, as soon as you apply gram schema on that matrix, on that users matrix, it will tell you how many unique type of users exist in your data. Understood? That is why this is so profound. That is why this is so important. And I told you rank is nothing but the unique information that matrix tells you. Right now you have the unique information as U1 and U2. And the second part, the question that you are asking, how do you project V3 in the direction of, this is what we all learned, right? This is all what we have learned. Projection of V2 in the direction of U1, how do you project? And as soon as you take a difference of the vector itself with the projection of that same vector on the second vector, once you do this difference, the output becomes perpendicular, because this is what we have seen. As soon as, let's say, this is the first vector V, this is the second vector. As soon as, let's say, this is projection of V onto U, and this particular length, that dotted length, is nothing but V minus projection of V onto U. Okay, so this is what is perpendicular to U vector. So as soon as you subtract the vector from its projection on the second vector, you will eventually get the perpendicular vector. That's why they are perpendicular. The first question. Second is, how do you get to this formula? This formula is what we essentially nailed out at the very first step. Okay. The projection formula is this. This is how we got to projection formula, right? So we basically want a vector v in the direction of u. If that vector v has to be in direction of u, it has to be a scaled version of u. This is what you're seeing, the scaled version of u, right? So v minus alpha u is perpendicular to u, basically. That's what you also saw, right? This particular part, v minus alpha u, where my cursor is perpendicular to you, basically saying v minus alpha u dot u is equals to 0, or u transpose v minus alpha u is equals to 0. It's the same thing. The two different views of the same thing, right? Now, using the first form, you got to this part wherein you found what is that scaling thing. You got to this. From the second form, you have got to this. You can use any one of them, basically. Okay. And that's what the projection vector is. We have done nothing new here. It's just that we have found or we have discussed about a technique called as gram schemate, which given a set of vectors, think of it as you have a matrix of data points. Okay. And this is user number one, user number two, or whatever. Let's say a lot of people who are applying for loan in a bank. Okay. These are many number of users. User one up to every single day you have lakhs of users. Let's say some lakhs of users, right? Now, if the bank has implemented a method to find out what if the bank has implemented a method to find out automatically whether the loan should be approved for these users, the home loan should be, or whatever the loan they are applying for, whether it should be approved for these set of users or not. They have applied some automatic method, but they don't need to do calculation of each and every user. Once you find out that out of these users, lakhs of users, there are only 10 unique users which exist, u1 to u from u1 to u10. Once you know that there are only 10 unique users, you will just see which particular users are aligned with U1, which particular users are aligned with U2, which ones are aligned with U10. So you just need to find out these U1 and U10, and then you can build all the machine learning algorithm on top of it. So you don't have to actually deal with a very large matrix to develop an algorithm. You can deal with this small matrix of 10 vectors and do all what you would want to do. Okay, this is the essence of GS. But anyways, I'll open up to questions from all of you, and then we'll go into. I'll just discuss it for 5 minutes, okay? Because we have to cover a lot of things today. Yes, that's right. That's right, Amit. Go ahead. Whosoever is first.
Good morning, sir. Sir,
Good morning.
V minus alpha U, the projection, the subtraction you are taking.
Mhm.
Can you please explain on that? Should it
Okay.
be is calculated by Pythagoras because 90 degrees involved and then there's an hypotenuse created on.
See, if you get into trigonometry, if you think of it as you already know that, let's say that we get into the Pythagoras, right? So let's say that this is x, okay, and this is y. Now, what portion of x is aligned in y? That is x cos theta, isn't it? Right? This angle is theta. This length basically is x cos theta, right? And
Yes.
when you are looking into projection, the projection is also saying the same thing. It is the formula is x dot y divided by x dot x in the direction of y. This is that formula. The top thing is what? X dot y is what? X y cos theta. If you think of it, which is nothing but x cos theta into y, right? You can rearrange them, x cos theta into y divided by x dot at. Basically, why you are looking into x, sorry, divided by x, the first vector, yeah, divided by x dot at, because you are looking into the length. You are normalizing the vector. You are normalizing the length of the vector. So that's why this is just the denominator is just the normalization thing, and in which direction it is aligned to. Okay, so it is all part of the same thing. It's just that we are looking at it from a different perspective. So the angle is already 90 degrees. It's not 90 degrees. So one other view is, if you think of it, the 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 animation that I draw here, the dot product, right? If you think of it, the projection is always perpendicular. Whatever is that case, wherever you move to, it will always be perpendicular. Here in any of these cases, whenever I move the first vector, or if I move the second vector, the projection would always, let's say, if the first vector is longer than the second vector, then the projection would be projection. Think of projection as the shadow of first vector in the direction of second vector. That's how you can easily get to. When you look into shadow, it is all perpendicular directions.
So thinking in Pythagoras theorem is a wrong, thinking here, right?
No. The Pythagorean theorem is also right. It's just that you will have to deduce that formula using Pythagoreans. You can actually get to that. I don't want to get into it right now because it will waste a lot of time.
Okay.
But it's the same
Sure,
thing.
sir.
It's a different view of the same thing. You can get to the same thing using same formula using Pythagoras as well. And
Okay, sir.
again,
Thank you so much.
just the sake of understanding, let me tell you, when you, and this is what may clarify your intuition. When you write v dot v, what is v dot v? V dot v is nothing but the length of v vector, right? Because if you think of it, v dot v is much amount of v vector is aligned with itself, and you already know that. Let's say if v is v1 and v2, okay, when you multiply v1 and v2 with itself, v1 and v2, what do you get? You get, let's say this is two-dimensional vector. The v vector is two-dimensional vector, right? So when you take the dot product between them, it comes out to be v1 square plus v2 square. Now v1 square and v2 square, let's say that this is v1, this is v2, okay? This is v1. Now this is the vector, let's say this is the vector v1, some v1 and v2, right? Now what is v1 square? V1 square is, v1 is this, v2 is this, v1 square plus v2 square. This is v1 square. So let's say, for example, what is the length of the vector? Length of the vector is from that height, from the right angle triangles, or let's say the Pythagoras theorem thing, right? So v1 square plus v2 square is this hypotenuse, which is right angle triangles. Now v dot v is nothing but v1 square plus v2 square, which is the hypotenuse here, right? Because this is v2, this is v1, and that's what you're looking into. So basically, dot product is nothing but a generalized version of Pythagoras. This, you just have to look into it from that perspective. Okay.
Okay, sir. Thank you.
Go ahead. Second question, please.
Yeah, sir. Sir, I'll go quickly. So in this, when we are trying to find U3, that is the projection So we are subtracting from V3 the projection of V3 with respect to U1 and projection of V3 with respect to U2.
U2.
So sir, my question is, yeah, why U2 here? Why not V2?
See, firstly, think of it as you have three different vectors, these three. Okay, let's say that you first projected this vector in the direction of the second vector. Let's say that this is V1, this is V2, this is V3. Okay. Then as soon as you took the difference, you found a new vector. You named it as U2. Okay. You found U2. Let's say that this is U1 in the direction of, or let's say this is U2 and this is V1. V1 vectors. Let's say that this was the first vector. Or let me do it. Let's say that this is V1, this is V2, and let's say that this is V3. Okay. Now you just take what we did. We took firstly we named V1 is equals to U1. So this is the direction. Okay. Now what we did, we took the perpendicular of V2 with respect to this, just to take how much of V2 is aligned in the direction of V1. That's what we did. As soon as we subtracted this length or we found this perpendicular direction, we found that this is that vector. This is that vector. Now we found that this particular vector U2 basically is perpendicular to U1, right? You found that U2 is perpendicular to U1. Now, if I have to find V3, a new dimension, it has to be perpendicular to both U1 and U2. And that's why you will have to subtract how much amount of V3 is aligned in the direction of U1 and how much amount of V3 is aligned in the direction of U2. Right, such that then you will be getting the third vector V3, which is perpendicular to, actually in 3 dimension, it will be in 3 dimension. In 2 dimension, you will not get the third vector is automatically independent in 2 dimensions. Okay, so when you talk about three vectors in 2 dimensions, you can never get to those positions wherein the three vectors, let's say these three vectors, they are all mutually perpendicular. This is the case that can happen. This is how they can look like. Or let's say, for example, a mutually perpendicular case can only be like this. The only way that can happen is we are looking at three-dimensional point of view. Three vectors are perpendicular to each other only when you have the third dimensions, right? So in 2 dimension, you cannot have three vectors which are mutually perpendicular to each other. So what basically, coming back to your question, what we basically were doing is we are finding how much amount of V3 is aligned in the direction of U1. So that we are trying to find out V3 perpendicular to U1. And then we are trying to find out V3, what portion of V3 is perpendicular to U2. That's why we are doing that subtraction of V3 from projection of V3. Firstly, you are finding out uh, how much V3 perpendicular to U1, the first part. Once you do that, then whatever remains, you're just finding its projection in the direction of U2, because you want that the new vector to be perpendicular to the second vector as well. And that's what you're doing here, right? Good.
Yes, sir. I understood it. Thank you.
Next.
Did not understand the last part. So
Hello, sir.
finally, after
Hello, sir. I have a
Yeah.
question, sir.
Yeah, go
Hello.
ahead.
If we have n number of features, then we will
Mhm.
find the respective projection for each vector with respect to every other vector.
That's right. That's right.
Uh, Sir, I have a question.
Yeah.
Sir, like you said that V3 is like dependent on V1 and V2, and that's why V1 and V2 are basis vector. But we can write any vector in combination of any two, right? So any two vector can become a basis vector.
You see, firstly, you'll have to understand that basis vectors can be infinite.
Okay.
Okay. So there are no finite vectors. The best possible basis vectors in 2 dimension is these. 1 0 0 1 and 1 0. Right, these two are the basis vector, the best, because they are perpendicular to each other. You can, using these two vectors, you can actually define any linear combination of these vectors, can you can reach to any point. These are best possible basis vectors, but it doesn't mean that this particular vector, these two independent vectors, are not basis vectors. They can also be basis vectors. It's just that they are not perpendicular. So there are infinite basis vectors that you can create. The definition of basis is a set of vectors using which are linearly independent and using which you can span the entire space. So let's say if you have three-dimensional vectors, 1 0 0 and 0 1 0. Okay, let's say that these two vectors are independent, but can we span the entire three-dimensional space using these two vectors? No. So they cannot form the basis, because you need the third dimension as well. You need the third vector as well, 0 0 1. Now using these three vectors, you can span the, or you can reach to any possible point in three dimensions. That's the definition of basis, is the vectors has to be independent, and using those vectors we should be able to span or reach to any point in that space that these vectors reside. Because we are talking in terms of R3, these three vectors would help us reach to any possible point in three-dimensional world. Okay, so any vectors which are there that can exhaust the entire space, they would be basis vectors no matter what. So in any space, there would be infinite number of basis vectors. So in this particular case, these two can also become basis vectors, v1 and v3. Given that they are independent, and using them you are able to exhaust the entire space.
Sir, finally we got U3 as zero vector. Then you were
Right.
saying that the rank is 2, but rank should be 0 there. Why we are referring
Oh,
to the starting point of V1 and V2 in
right.
that case?
Right. See, rank means when you look into a matrix, let's say we arrange those vectors in this format, whatever we had, 1 1 0, 1 1 0, 2 0 1, and 2 0 1, and 3 1 1, right? So this is a matrix. Now you already know that rank of a, let's say this is a rank of a matrix A, is how many unique information does this matrix possess. In this particular case, you know that, firstly, you already know that the third column is just an addition of the first two columns. So going forward, the intuition is rank should be 2. The maximum rank is 2 here, because there are only two unique information, two unique columns that you
Right.
have, right? And that's when, even though we reach to U3 as 0 0 0, but we know that U3 has the dependency in terms of U2 and U1. You already knew that. And U3, what gram schema does, it tries to find out how much amount of overlap does this vector has in the direction of this vector and in the direction of this vector. Now what you have found is there is no new information in U3. Basically, all that information that is coming in U3 is coming from the first two vectors itself. That's why you got nothing new in U3. Now, the only unique information is U1 and U2. Hence, the rank is 2.
Okay. Okay. So, taking your example to find the unique users for Netflix, so Schmidt will keep on calculating the projection, and then removing the portion which is aligned, and finally, what we end up with, if we end up with zero vector, then we say that this is not aligned. The other two, the remaining would have been aligned, right?
Right, right.
Okay. Okay.
Keep doing that.
And
Yes.
remaining would have been unique also.
Right.
Okay, okay.
Exactly.
Yes, thank you.
Yeah, go ahead.
Yes, sir. A quick
Just
question just to understand this. So this is the overall exercises to basically reduce the number of dimensions and then reduce the complexity of matrix that we are gonna use in our model. So that is why we are trying to remove the redundant features or columns. Is that a
right.
correct
Exactly.
understanding? Yeah.
That's
Okay.
right. That's absolutely right. So when you start with your machine learning model, what would happen is there are generally, I told you that the intuition from the user's point of view, but think of it as when you say, let's say, salary of an individual is dependent on their age, the number of certifications, the gender, the XYZ experience, and so on. But there could be unique information like age and certifications, but there could be some dependent information. Age and experience are extremely dependent to each other, right? So if you have to remove any one of them, which are not, or anything which is correlated, in that case, you will use the same thing to find out what exactly is the unique features, what exactly is the unique set of features in my model, so that you can start with a unique set of features from the very first step.
Great, yeah.
That's
Thank
right.
you. Just one more aspect from, again, I might have to go through the overall the vectorization form of it. But if we are comparing two vectors and then we took the x-axis, one in x, another in y-axis, let's say, and we are finding projection of y on how much y is aligned to x, right?
Mhm.
What happens if my x-axis has a shorter vector? So how can we avoid those situations? Well, in practical sense, like if we are
Right.
comparing two, the one in the y should be generally smaller than the one in x, right? So, but how do we looking at real data? Is that a correct understanding, first of all?
Yeah.
Like here, when
See,
we are doing the projection, yes.
right.
Go on.
Yeah. In this particular part, see, the only thing that you need to look into is there is the first vector is longer than the second
Correct,
vector. Okay.
correct.
There is more uniqueness in the first vector than in the second vector. That's what you can also relate to is. Now, when you take the subtraction, you are finding that there is very small overlap between first and second vector, which is the second vector itself. But all that uniqueness is coming from the first vector. That's what you will
Mhm.
get to. Okay. So you don't have to start. You don't have to align with what is the largest vector in my data set, and then
Okay,
subtract that. So
okay,
you don't have to get into that part, because eventually what you mean is what are the unique directions in my data. So
okay,
basically, once you get those unique directions, you can actually, will be eventually learning. This is still the initial, these are still the initial building blocks of what we are going to learn next. But think of it as you are getting new unique directions, new unique dimensions, using which you can actually create much more better model in your machine learning than having dependent directions in your model. Okay.
right, right. Again, just like if we increase the V2, like if I increase the V2 greater than V1, would that be, maybe we can have those kind of cases, right? If we look at the data. So,
Yeah, yeah.
yeah, so if we increase the V2 over V1, uh, is that a logical scenario or can this happen or this is
This can happen.
something?
This definitely can happen. That's this. There are cases wherein let me take the last question and then we'll get
Sure,
to
sure,
the
sure,
UD
sure, sure.
computation part.
Yeah,
But that is most
thank you.
important from your assignment point of view. Yeah. Go ahead. Whosoever is the last question.
Hi, sir. Sir,
Hi.
in your third example where you showed where we have to remove the overlap of V3 from V1 and V2.
Hmm.
So in that we took V2 as 1 minus 1 and 1, which was actually V2 minus projection of V2 from V1. So
You,
why we took this 1 minus 1 and
right.
1? I'm not able to
See,
understand.
think of it as first, given the three vectors that you have, let's say that these three vectors. Firstly, what you did, you just concentrated on these two vectors, made them
Hmm.
perpendicular, mutually perpendicular to each other. That's
Yeah.
what the first step did, right? Now,
Yes.
the third vector, you need to find out how much. Now, you don't want to see how much of this vector is aligned with, let's say this is the first direction, and you found the next direction as perpendicular. Now this is the third vector. Now you would find out how much is this aligned in the direction of this vector, and how much of this is not aligned in the direction of the second vector, which is this, because you already found two independent directions. You would want to find out how can I make this 3 v3 align in such a way that this it becomes perpendicular to the first two ones. Hence, this was the U1 we got, this was the U2 we got. Hence, we rotated it in such a way that it becomes perpendicular to make it perpendicular to the first two perpendicular vectors. Okay, not the V2 vector. Reason being, it will not be perpendicular. We already have found the new directions which are perpendicular. Now we are rotating the third vector in such a way that it is perpendicular to the previously found vectors or previously found directions. Now we found that it is because it is dependent. There is no new way. It is only the origin which is perpendicular to these two vectors.
Okay.
That's what you found out. Eventually, what you are trying to do is once you have found out new directions from the very first step, let's say the third vector is there. The only thing that you are looking into, let's say these were the vectors using which it's not this one. Sorry about that. So these two were the vectors. Okay. These two the initial vectors. But eventually what you got to, you this vector, which is the direction, you have
Somehow
got
screen
these two
got
vectors.
froze for me.
Is it? Is it for everyone?
Yeah.
It's visible.
It's visible, right? Okay.
Okay.
The third
Maybe
vector
some
that
network
the
issue.
third,
Mhm.
yeah, yeah. The third vector is what you are trying to do is you are trying to just take the third vector wherever it is perpendicular to the first one. What you are trying to do, the given vector that you had, let's say U and V1, you'll start with the new direction that you have got, which are U1 and U2. Okay. Anyways, let me get to the next part, which is important from your assignment point of view. Now we are getting to come back to you. Maybe towards the end because we only have got 40 more minutes now, 40, 50 more minutes now. So the very first part is LU decomposition. Uh, Position. You need to understand what exactly is decomposition. When you multiply two matrices, think of it as A, B, you get a new matrix. When you multiply a matrix A with matrix B, you get to C. Okay. So basically, I told you that matrix does different types of transformations. Let's say A matrix rotates the entire space. Let's say that this is the entire space, two-dimensional space. A matrix could rotate it 45 degrees like this. Now the B matrix could stretch it like this. The entire space, this is this is your x and y axis. This is what space was with the rotation, sorry. This is what your space was with the rotation. Okay. You have rotated like this. Now initially your space was this. What happened? I think the screen is not visible, is it? Just give me a moment. Let me see what is this show. Screen is frozen. Stop and share. Is it visible now? It's all good. Do you see? Are you able to see me writing and something on the board? Yes. Are you able to follow that? There's a lag. Just give me a moment. I think there is a problem with respect to the Wi-Fi. Am I audible? Good, well, now. Are you able to follow my screen now? Well, is there still a lag? Let me reshare. Let me refresh as well. Okay. Okay. Audible but lag. Now I think you will not have any lag. I have just switched to my Wi-Fi. The only problem is the electricity here in the place where I am in, it keeps I mean I didn't wanted to use my Wi-Fi. It is much better than my hotspot, but I think there is some issue. But anyways, let's get into it. I think it will not cause any issue until we have electricity disruption. Okay. Okay, got it. So let's say I was just telling you that matrix decomposition. What basically is decomposition? Decomposition. Decomposition is firstly, for to understand decomposition, you will have to understand what is composition. Composition is when you have two matrices, let's say A and B. When you multiply them, you will get to C. Now, when you multiply A and B, you get to C basically whatever C is doing. You already know that a matrix gives you different types of transformation. It can shear the space, it can rotate the space. Think of a A4 sheet of paper which is of rubber, right? You can extend it from diagonal and then it will get stretched like this. When you stretches it from this horizontal axis, then it will get stretched like this, right? So this is what it would happen. It can deform like that. You can also rotate it and it will get rotated like this, the same sheet of paper. So there could be stretching, there could be shear, there could be also shearing. Think of it as this is your initial space. You just have sheared it a little bit. Okay. So there could be shearing, there could be stretching, there could be rotation. So all of these things are possible. A matrix can do anything, any of that, right? So this is what you would have already visualized here. Think of it as these are the matrix element. Okay. Now if I change these elements a little bit, let's say that this is what the first element is minus 1.62. The second element is in that row 2.11. In the second row minus 0.87. And the second value is 1. So this is that matrix. Now what sort of transformation does this matrix does? This is the type of transformation it is doing. Now you're seeing that there are multiple things involved. There is some sort of rotation. If you see here, there is some sort of rotation. Okay. And then some stretching. So there are combined effects involved in this matrix, right? So you are rotating the space and then you are stretching the space. The composition basically is, just give me a moment, just a minute. So when you basically are looking into matrix, see that this entire matrix, you don't know what type of transformation it is doing. And that transformation could be fragmented into basic type of transformation that you know. Rotation, shearing, rotation, stretching, shearing, whatever. There could be two different types of transformation embedded in one matrix itself. And that's what you're seeing here in this matrix. The elements of these matrix are doing that type of transformation, right? So if you look into it closely, a matrix can bring in a very, I would say, some very different transformation that is unimaginable. Let me show it to you something else. Let's say that this is the kind of transformation wherein you are flipping the entire space as well. So this was your input space, and now you are just flipping it, right? So and then stretching as well. So there are different types of transformation which might be very difficult to understand. Now what matrix decomposition does is, matrix decomposition, it basically helps you find out, let's say given a matrix C, if you decompose it into um, basically uh, primary matrices A and B, such that, let's say A matrix does only rotation. Okay, B matrix only does stretching. So you already know that C matrix, which is obtained from A and B by multiplying A and B, it will basically represent both of them in a combined way. So that is what is decomposition. Decomposition is what basic transformation this matrix does. Okay, now you already know, I gave you um, this intuition in the very first class, right? Ax is equals to b. When you multiply a matrix A with the vector x, you get to a new position B, right? So this is what you already know. This is vector x. When you multiply, let's say that whatever this matrix is, the vector gets to a new position B. Now this new position, think of it as You can also relate to it as the matrix A is, let's say that this is the rubber sheet of paper wherein this vector was already there, or this vector was already there. Okay, this is the same vector, for example. When you expand it from this side, or let's say some sort of stretching of this rubber sheet of paper, this vector moved to this new place. This is the B vector now. Not so basically, you can think of matrix A as doing the transformation to the entire space such that the vector is getting dislocated. You can also think it like A is pushing X to B, but you can also think of it like A is doing the transformation to the entire space such that every vector is getting dislocated, right? That's what is shown here if you think of it in this particular case, right? So let's say that whatever this vector is, V vector, okay. Now you will get to see how does that V vector gets shipped to a new position. This is look into MV, which is what your vector is. How does that vector moves to a new position? Because the entire transformation is happening. This might go outside the pane itself, so it is outside right now. But you were able to see this was your previous vector. The entire space changed, and hence this vector changed. Right? That's what it is. So every matrix brings some sort of transformation, but transformation are very difficult to, let's say there could be some complex transformation. This matrix C might be bringing in some complex transformation. Now, if we know that this complex transformation can be actually decomposed into simple transformations, like A could be only doing rotation, B could be only doing stretching, then that becomes much easier for us to understand what exactly C is doing, right? That's why decomposition is important. But the other perspective also is, if you look into it, a set of linear system of equations, Ax is equals to B, right? When you have a set of linear system of equations, Ax is equals to B, you write it in this way. This is the matrix form of writing the same set of equations. But what you're saying is what matrix A gets multiplied to X such that you transform X to B. Okay. Now, to get to the solution of this, you already know that you have some things that you have already learned, right? To solve a linear system of equations like this, what is the algorithmic way that we have learned till now? Gauss-Jordan elimination, right? Exactly. So Gauss elimination, Gauss elimination is what you already know. To get to the solution of it, you already know Gauss solution and Gauss elimination. But the algorithmic way of doing that is REF, right? Ecklian form or row Ecklian form, right? And then you have already learned, also learned reduced row Ecklian form, REF or RREF. You know that that's basically is the same Gauss-Jordan elimination that you know. But to solve it, you do this. Let's say that I want A to be decomposed in two simpler matrices L and U. Okay. L is a lower triangular matrix, U is upper triangular matrix. That's why L. L is lower triangular matrix, U is upper triangular matrix. You know what essentially is a lower triangular matrix and upper triangular matrix? Lower triangular matrix is, let's say that if you have a matrix like this, uh, if you have elements, let's say that 1, 2, 1, 0. So if you see everything above the diagonal element are 0, and below the diagonal element there are non-zero elements. If you have something like this, wherein that in the triangle below the diagonal element, if you have something which or the elements are non-zero, then we are speaking about lower triangular, because there are in lower triangle there are elements which are not all essentially zero, right? If you have a situation like this, let's say that we are talking about 3 by 3 matrix, 2, 1, 0, 0, 0, 1, 4, 0, well, not 0, let's say that 4, 0. Now, if you look into this diagonal elements here, everything above is 0 above this diagonal element. But below, you have elements which are essentially not 0. So this is a lower triangular matrix. An upper triangular matrix would be something like this, wherein you have 1, 2, 2, 4, 5, 6, let's say, and this is 0, this is 0, this is 0. Now you see that everything below it is all 0. But the important part that we are looking into is the element which are non-zero. So this is upper triangular. This is lower triangular. Okay. So these are called as upper triangular and lower triangular matrices. Now, what we are saying is, can we decompose A when we write Ax is equals to B? Okay. Can we decompose A such that I can write A into a lower triangular and an upper triangular matrix such that this entire equation becomes Lux is equals to B? Now, there is a simplification why we are writing it, but you will eventually understand that whatever you have done in REF or RREF, whatever it is, this essentially is matrix way of doing the decomposition. So what I mean by that is, think of a simple matrix for now. And the simple matrix is, remember this equation, okay? LUX, which is lower triangular, upper triangular multiplied by the vector, getting to a new vector. Let's look into a matrix. A matrix is, let's say, 2, 1, 4, 3. Okay, and this is the matrix. Now let's say that to do or to get to the reduced Euclidean form, or not reduce, but let's say row Euclidean form, because I don't want to divide but 2 by 1, 2 by 2. So let's say that I want to do an Euclidean form of this. To do an Euclidean form of this matrix, or to find the Euclidean form of this matrix, what do I need to do? I need to do elementary row transformation, which would be R2 is equals to, what would be that transformation? In this particular case, what would be that transformation, elementary row transformation? R2 is equals to R2 minus 2R1, right? R2 is equals to R2 minus 2R1, right? And in that case, what would eventually happen? You are going to get 2, 1, 0, and 1, right? So this is what you will be getting. Now, what type of matrix this is? Do you see a special type of matrix? This has become, whether it is upper triangular, exactly. So this has become an upper triangular matrix. While doing Euclidean transformation of A, what you eventually get to is, the goal is to transform A into U. Okay, the goal of Euclidean form is transform A into an upper triangular matrix. That's all. That's all you are doing in your Gauss-Jordan elimination. So basically, you are transforming A into an upper triangular matrix. But while doing all of that, what you did, think of the multiplier that you used. Okay, the multiplier right now is 2. Okay, and think of it as not minus 2, but the multiplier itself is 2, right? So what if I take an identity matrix? Think of it as 1, 0, 0, 1. This is the identity matrix. The lower triangular matrix would have been this. Let's say that whatever I have taken as multiplier to do elementary row transformation, I have replaced the value in my lower triangular matrix with that multiplier. Okay, now let's look into this multiplication. 1, 0, 2, 1 is my L matrix. When I multiply with the upper triangular matrix, which is 2, 1, 0, 1, what do I get? So let's say 1 into 2 plus 0 into 0, which would be 2, right? Then 1 into 1 plus 0 into 1, right? So it would be 1. Then 2 into 2 plus 1 into 1, 2, 2 into 2, sorry, 2 into 2 plus 2 into 2 plus 1 into 1. Sorry. 2 into 2 plus 2, 1 into 0. It should be 4, right? 2 into 1 plus 1 into 1. it should be 3, right? So what you have got, you have got 2 4 2 1 4 3, which is eventually what your A is, right? So basically think of it as what we are doing. LU decomposition is a compressed, or let's say it's a Gaussian elimination itself. It's a way of doing Gaussian elimination. That's what you have learned. Now, Gaussian elimination basically transforms A into U. Now, all the multipliers that you have used while transforming A to U, all the things that, let's say, you always do R, let's say Ri is equals to, let's say that these types of transformation you do, Ri is equals to Ri minus M times of Rj. This is what you'll be doing. Just keep a track of which M's are you using. Once you know which M's are you using, you compose your lower triangular matrix with those M's. That's all. That's all you have. So once you compose them, those M's into L, and you already are transforming in while doing Gaussian elimination A into U, right? So you get to L times U is equals to A. Right. Now, the essence is not to transform A into LU. The essence is because A is equals to LU, LU times X, because we wrote AX is equals to B. So LU times X is equals to B. Now, because this is lower triangular, upper triangular, it becomes much easier for us to solve this equation than what we would have been doing it here. Because firstly, there are too many zeros here. Okay, the calculation becomes easier and faster. Apart from calculation becomes easier and faster, I'll tell you about to compute, to get to whether it is consistent or not, you eventually find out what is the determinant, whether the determinant is 0 or not, right? So finding out determinant becomes very easier in these types of matrices which are lower triangular and upper triangular. I'll get to that, but just to give you a perspective of what exactly this is, again to help you understand what exactly this is, think of the same matrix that we took, which was 2413. 2143. Okay, this is what the matrix was. Let's think of the identity matrix. Let's say I into A. What would be the multiplication of I into A? It should be A, right? Because identity matrix does nothing, and that you can also visualize it here. I mean, when you look into identity matrix, you just change 0 1 this to 1 0. And 0 1. Sorry, almost there, right? So you are able to see that 1 0 and 1. Sorry, this is 1. Now you are able to see that this is the entire two-dimensional grid that you have. There is some mistake that I have done, but let's say that this is 1001. You see that there is no transformation that it does, right? And that's what you are seeing. So when I multiply a matrix with identity matrix, there is nothing which happens. Just like when you scale 2 with by multiplying it to 1, this it doesn't scales to 1, doesn't scales to. That's what identity matrix also does. It doesn't does anything. Okay, but think of it as when you are looking into the identity matrix 1001 multiplied by 2143, you are eventually getting 243. You can actually do that verification. But here the identity matrix basically is 1001. Now let's say that we do the same transformation to this identity matrix. Okay, the kind of transformation you will be doing on A, the transformation that you all told me was R2 is equals to R2 minus 2 into R1. Now let's do that transformation to this identity matrix. What eventually would happen? R2 is equals to R2 minus 2 R1. This would translate to the first row would remain the same. This would become minus 2. This would become 1. This is already 1, right? This matrix that we get to is called as elimination matrix. Okay. Now this elimination matrix, you are already seeing there is minus 2 here, right? And that's what you did in this part. So this elimination matrix, if you think of, if I use this matrix I, elimination matrix, let's say I call it as E. If I multiply E with A, let's see what it will give me. E times A is nothing but 1, 0, minus 2, 1. This is the E matrix. I multiply it with A, 2, 1, 4, 3, 4, 3. What do we get? 1 times 2 plus 0 times 4. It is basically 2. 1 times 1 plus 0 times 3. It's 1, right? And then minus 2 times 2, 4 plus 4. It's 0. Then minus 2 times 1 and minus 3. Basically, minus 2 times 1, it would be 1 only, right? So eventually you are getting this. Now, what is this matrix? Have you seen this matrix previously? You saw this matrix here, which is your upper triangular matrix you'll reach to after doing the row transformation of A, right? So basically what you're saying, elementary matrix A multiplied by A is equals to U. So when you keep track of how you are doing your elementary row transformation and you give it a matrix form, then basically your goal is to reach from A to U. But these elementary metrics keeps a track of what you are doing in your elementary row transformation, because this is what your scaling factor is. Row 2 minus 2 R1. This is your minus 2, right? Or else what you can say is, think of it as, in this was a simple case. We were able to get to the upper triangular matrix only with one transformation, but you eventually keep doing this multiple number of times. There could be multiple elementary matrices. Think of it as E1, E2, E3. There are three transformations that you did. Okay. And then you multiply it with A, you eventually get to U. Okay. Now, or else what you can write it as is A is equals to E1, E2, E3, whole inverse of U. That's what it is, right? Or you can say that L is equals to E1, E2, E3. Let's say that there are only three transformations that you did. L is equals to this, and U is what you have, right? So this is all the set of row transformation that you're doing. If you keep that matrix, take the inverse of them, multiply those matrices together, take the inverse of them, that basically is your L matrix or lower triangular matrix. So this is essentially speaking what your LU matrix, what when you decompose A is equals to LU, LU is the transformation history, whatever transformation you're doing, or let's say all the values that you are taking to scale and do the road elementary road transformation. It's keeps a track of how we did elementary row operation, right? U is the output that you get to. Basically, you eventually want to reach from A to U, and that's what your staircase pattern also does. Remember that we had the pivot element, we wanted to make everything below it as 0, then the pivot element, everything below it as 0. Eventually, when we do this staircase pattern, what we get to, we get everything in below the diagonal element as 0, and everything above the diagonal element not necessarily all 0. So basically, you get to upper triangular matrix itself, right? So A is equals to L into U. This decomposition is nothing but RREF or REF decomposition itself. It's a matrix way of writing the same thing. It's a Gaussian elimination complex in matrix form. That's all. Okay. I wanted to actually do a problem, but I will run out of time in this entire thing. So let's say that, just to help you understand, quickly doing it 5 minutes. Let's say that you have a matrix, okay, 2, 4, minus 2, and let's say 1, minus 6, 7, 1, 0, 2. Let's say that you have this matrix. The goal is to reach from A to U, upper triangular matrix, right? How do you reach to that? The very first thing that you will be doing is R2 is equals to R2 minus 2 into R1, right? And here in the second would be R3 is equals to R3 plus R1. Now this is what eventually you will get to. So let's say that The first row would be 2, 1, 1. This would becomes 4, 0, 6, minus 6, minus 2, minus 8, minus 1, and this would eventually become minus 2. Okay, and same goes to this particular part wherein you have this as 2, 2, 2, 0, 7 plus 1, 8, and 1 plus 1, 3. Now, to make next pivot element is this, right? Non-zero element in the in the second row. You found that the pivot element here moved everything as 0. I do not have the time to get to your question. You can write these questions to me. Okay. So then you have found the next pivot element as minus 8. You will make this as 0. So what you will be doing? You will be doing R3 is equals to R3 plus R2. Okay, in that case, this becomes 2, 0, 0, 1 minus 8. This becomes 0. This was 1. This is minus 2. 3 eventually would become R3 plus R2. This will become 1, right? Now, this is what you have got. But keep a track of what you did. Minus 2, here 1, and here 1, right? So let's say, for example, you can, if you write it like Rj is equals to Rj minus M times Ri. Okay, in that case, whatever you have here, okay, this M form, you have to compare it with this unique form. So your M multipliers are nothing but the first multiplier that you have is 2, which is, let's say, we call it as M21. The second multiplier that you have is here you have, if you compare this with this, you will get multiplier as minus 1. The third multiplier that you have got, this is 1, sorry, not 0. Third multiplier that you have got, M32 is equals to minus 1. Now, these are the three multipliers. So the lower triangular matrix would be of this form. Because you have lower triangular matrix, firstly, just create 1, 1, and 1, and 0, 0, 0. Now, what you have, M21 is 2, you place it here. M31 is minus 1, you place it here. M32 is minus 1, you place it here. So this is your lower triangular matrix, right? You keep a track of what you have used to do the road transformation, that's all. And then you compare it with this standard equation. You get to what is the value of M. The value of M in the first one was 2. In the second one, because it was R3 plus R1, hence that we have found it as minus 1. In the third one, we have R3 plus R2, hence we have found it as plus minus 1. You can also take a look into it from that perspective, because you have E1, E2, E3 into A is equals to U, right? That's what we looked into. And there are three different transformations which are happening, three different elementary operations which are happening. These are elementary operations stored in the matrices. Okay. And E3 is basically the matrix with only M21 place. E2 is the matrix with only M31 there. E1 is the matrix with E32 in this one place. Now, when you multiply them all together with A, you get to upper triangular matrix. And your upper triangular matrix is nothing but this one. That's what you have. Okay. So A is equals to LU. What it does is L keeps a track of the transformation history, and U keeps a track of simplified the output that you're getting. Okay. That's what is LU transformation. There is nothing more than it in LU transformation. Okay. Now, when I write it like this, you can also write it like this as well. A is equals to E1, E2, E3, whole inverse into U, right? And that's why you see that you are getting to these minus values. And because when you have it all of them in the on the left hand side, you can take L as like this. Okay. When you took the inverse, they basically becomes 2 minus 1 minus 1. And that is where that minus comes from. That is where we are comparing Rj, or the equation with Rj is equals to Rj minus M times Ri. Okay. So this entire M value, the reason that we are comparing it with minus sign is we are doing inverse of these matrices. And that's why this minus comes. But anyways, this is what you will eventually understand. Keep doing all of them. Keep track or practice one of the problems which I'll be sharing. You will get to understand what exactly it is. But the simplest understanding that is, you keep a track of what you used as a multipliers. That's all. And then use them in to compose your L matrix. Okay. Now, when I told you that that A is a simple matrix right now. It could be a 3 cross 4 matrix. It could be a 5 cross 3 matrix. It could be 10 cross 11 matrix. A doesn't has to be, when you do not have the number of rows equals to the number of columns in a matrix, we call them, these types of matrices, as non-square matrices. Okay. Now these matrices are called as non-square matrices. When we have matrices like A, where the number of rows is equals to number of columns, or we call it as n cross n, these matrices are called as square matrix because the number of rows and columns are equal. So these are called as square matrices. Now, for do you know any specific type of square matrix that we have studied till now? Any specific square matrix that we have studied till now? Do you remember anything? Symmetric, yes. Symmetric matrices, that's right. Symmetric matrices. Now, they are square matrices, which is right. But symmetric positive definite matrices, they also are very essential. This is what you will eventually learn. But in lecture number 6th and 7th, actually 7th, why symmetric positive definite matrices are very important. So let's say any matrix which are symmetric and positive definite. We looked into positive definite matrices as those matrices where the determinant is always greater than 0, right? It's not equals to 0. So determinant is always greater than 0. Those are positive definite matrices. The other property of positive definite matrices are they have their eigenvalues, all of them as positive. Okay, and you will eventually learn about it in the next class when we'll be doing eigen decomposition. In this class, I wanted to start with it, but we have only few minutes. Let's see if we will be able to do that or not. So symmetric matrices, or symmetric positive definite matrices, SPD matrices. These matrices, when you are doing elimination, like sorry, when you're solving an equation like Ax is equals to b, such that A is a symmetric positive definite matrix, such that determinant of A is greater than 0, or the eigenvalues of A is all positive. You call them as symmetric positive definite matrix. But when you have this particular case, then the LU decomposition that you have looked into, think of it as if A is a symmetric matrix, its lower transformation, lower triangular, or let's say upper triangular matrix would be nothing but its transpose of L, right? So the upper triangular matrix would be nothing but the transpose of lower triangular matrix. Okay. Now, because A is symmetric positive, think of it as if you take transpose of a matrix, symmetric matrix, let's say 2, 1, 1, 2. This is a symmetric matrix, right? Whatever you do, if you take a transpose of the F, it would look the same, 2, 1, 1, 2, right? So when you have a symmetric positive definite matrix, what happens is you are basically in LU transformation, you are doing LU times of X is equals to B. You are breaking A into LU. L is the transformation history, all the values that you are taking to do elementary row transformation, the output that you get to. But what we are saying is when A is symmetric positive definite matrix, then in that case, U is nothing but L transpose. So A becomes L into L transpose. This type of transformation, when you are decomposing A is not transformation, this type of decomposition, when you're decomposing A into L transpose, this is called as Cholesky. So there is no difference between Cholesky and LU. It's just that we are talking LU transformation in terms of A being a symmetric positive definite. If A becomes symmetric positive definite, then if A is equals to LU reduces to the form A is equals to LL transpose, where U is equals to L transpose. That's all. So you don't have to actually uh, uh, get to that part wherein if you have already found you can get to the second part by taking a transpose. That's what it is. But eventually, this is what you need to know. Your assignment is all based on what you have learned here, this part. Okay. Your assignment is based on that. And the second part is the Cholesky decomposition is A is equals to L transpose. Now, to help you understand that, let's say that, let me see if I have Cholesky's example. Let me look into this. Oh, sorry. Sorry. This is a YouTube video. For example, this is the part. Oh no, what have they done? I want to use a simple matrix and show it to you. How does that decomposition looks like? Seems there is no place. Or let me go to my documents. So I think I have explained it better. So mathematical foundations, not here. Mathematical foundations, hidden channels, shared. So let's create a composition. So you see what exactly is Cholesky? I mean, Cholesky is when A becomes positive definite matrix, symmetric positive definite, then this Cholesky decomposition. A is equals to L transpose. Now think of these are the elements of the matrix. You can write L as L11 lower triangular matrix like this, right? So this is a simple way of imagining a lower triangular matrix wherein everything above is all zero. These are the values. If you take transpose, you see the transpose of that matrix. So you can actually find out how do you get to A11 by multiplying these matrices. So think of it as L11 square is equals to A11. That's what it is. If you multiply L11 plus 0 into 0 plus 0 into 0, L11 square basically is A11. So you can get to each value. How are you actually getting to A11 by multiplying these two matrices together? So this is that form. If you look at it, L1 is nothing but square root of A11, L21. You just multiply those matrices, these two matrices, then you can find out every possible value of these lower triangular matrices, L11, L21, L31, and so on, right? So you can use the simple way of doing it and then find out. This is exactly what is imagined or is asked for you in the assignment. You'll have to do the same steps that is listed down here to get to the matrix A by multiplying L into L transpose. This is called as Cholesky decomposition. But Cholesky decomposition, understand that this is nothing special. It is just that LU decomposition that you have learned, wherein A matrix becomes symmetric positive definite. So then in that case, the LU gets actually changed into LL transpose. That's all. That's what is Cholesky decomposition. Now, before we actually, I have only 10 minutes, but I would want all of us to understand once this is about lecture 4. I wanted to get to lecture 4 today. But this lecture 4 is talking about two different things. One is called as determinant. Okay. And the second is eigen decomposition. Position. Now, let me at least get you the intuition of determinants. Determinant, I told you, whenever the transformation is happening, the determinant is change in the volume or change in the area, right? So if you look into this particular part, you see this green region. So the determinant basically is during the transformation, how does this area scales, right? So if I change this, let's say that user you're able to see how does this entire green area changes. So in terms of 2 dimensional, it is area. In terms of 3 dimensions, it would be volume. In terms of n dimensions, it would be hypervolume. Okay. So determinant is nothing but the change in area, but there are various different formulations of it to calculate the area or volume while this transformation is happening. So determinant is, if you think of it as uh, the basic way of looking into determinants, you might have already looked into 2 cross 2 matrices wherein the elements are A, B, C, and D. Now the determinant of this matrix would be A, D minus B, C. This is what you already know. But how eventually we came down to this formula is what we are going to learn in next 5-7 minutes. I think it will not take more than 7 minutes. But think of it as we have to use 2 different things. One is called as minors, and the second is called as cofactors. Okay, minors is if let's say that we have a 3 cross 3 matrix, and let's imagine a 3 cross 3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 10. Let's say that this is the 3 cross 3 matrix. Okay, now in this matrix, if I am sitting at the element A11, which is 1 right now, at A11, if I remove the first row where that element belongs and the first column, the matrix that we get is 5, 6, 8, 10. Now, the determinant of this matrix is called as minor. So, or minor of A11. So, minor is basically the determinant of the submatrix, that you get to by eliminating the row and column at the position that you are calculating the minor at. So the minor at A11 is computed by removing the row where it belongs to, removing the column where it belongs to, and then finding out the submatrix and then finding the determinant. So what would be the minor in this case? For example, the minor would be 5 times of 10, which is 50, minus 8 times of 6, which is 48. So the minor would be 2, right? So basically, the minor at A11 is 2, right? So this is called as the minor is the determinant of the submatrix, or I can write it as minor of A11 is equals to 2. Right. So minor is determinant of some matrix by eliminating the row and column where that element sits. Cofactor is represented like this. Cij is equals to minus 1 to the power I plus j mij. So basically cofactor gives, if you think about it, if I'm using A11, I is 1, j is 1. So minus 1 to the power 1 plus 1 and M11. Now you already know what M11 is. M11 is this, the value 2, right? So cofactor would be minus 1 to the power 2 and 2, which is nothing but 2. So basically cofactor gives you positive or negative sign to your minor based on however it looks, it comes down to, let's say I plus j, because minus 1 to the power I plus j would always be negative for odd values. Minus 1 to the power I plus j would always be positive for even values. So basically, if I plus j is equals to even, then it's all positive. If I plus j is equals to odd, then it's all negative. And I'll bring down this to the volume or area thing. I'll actually connect both of these, the formula that you're using right now and the determinant idea that I gave you in the next session. But the formula for determinant using cofactors that you have just learned, this formula that you have just looked into, and the minor example that I gave you. So the determinant can of the matrix A, wherein the matrix A was nothing but 1, 2, 3, 4, 5, 6, 7, 8, 10. Now the determinant of this matrix is nothing but, let's say if I expand this matrix across the first row, the minor at 1, 1 would be 5, 6, 8, 10. The minor at 2, 2 would be just removing this and this. So it would be 4, 6, 7, 10. The minor at 3 would be remove the last column and first row, it would be 4, 5, 7, 8, right? You compute the determinant at each one of them. Okay. Once you compute the determinant, you basically can find the determinant as A11 times C11 plus A12 times C12 plus A13 times C13. So for this matrix, the determinant can be computed with whatever element that you used for computing minor multiplied by cofactor that you have used. Cofactor formula is Cij is equals to minus 1 to the power I plus j Mij. Okay. Then you do this, you add A12, the second element, which is 2 here, A12, multiply it with the cofactor. Cofactor would be computed using this formula. A13, the third element here, compute it via this. Now the determinant of A can be computed using the second row as well. So in that case, it would be 4 times C21 because the element is 4 here, plus 5 times C22 plus 6 times C23. Or determinant of A can be also computed by expanding it via the third row. In that case, it would be 7 times C31 plus 8 times C32 plus 10 times C33. Okay, you can use any one of these formula to compute the determinant. Either you expand it via third row, or you expand it via second row, or you expand it via first row. But think of it, if you are given a problem like this, 100,256,378. Let's say that this is what it is. Now, if I ask you to find determinant of matrix A, which row would you use to expand and why? Which row essentially you should be using? First, right? Essentially, because that's logical. You'll not have to even worry about the second and third. These two would become zero eventually, right? The only thing that you'll have to do is you'll have to compute the minor exactly at this position, which would be this, right? So it would be 1 times 5 into 8 is 40, minus 7 into 6 is 42. Eventually is minus 2 is what the determinant of the matrix would be, right? So you would expand it across the rows, or you can also expand it via columns as well. Think of it as Cij gives you the cofactor formula. Cij is equals to minus 1 to the power I plus j Mij. This gives you a checkboard like pattern because at this particular place it would be positive. The second, for the 3 cross 3 matrix, for example, it would be negative, then it would be positive. Here it is positive, here it would be negative, positive, positive, negative, negative, positive. So it is all alternating plus and minus that you will be seeing. If you have a larger matrix, you will see something like this: plus, minus, plus, minus, plus, minus, and then so on. Minus, plus, and so on, right? This is how it would look like eventually. So the formula that you have is not limited to what you see here. It will ever be expanding like this. Okay. Whichever row that you use, it would be expanding like that. And it's a recursive formula that you eventually see. Because why I say it's a recursive formula? Let's say that it's a 4 cross 4 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Now in this particular case, what would happen if you have to expand it via first row? Let's say you will first take the first element, remove these two, you will get to this matrix. Now, if you get to this matrix, at this matrix, you will get to 6, and then you will expand, let's say remove this row and this column, you will get to this one. Now you already know the determinant of 2 cross 2, which is nothing but AD minus BC. Now this AD minus BC formula, if you think about, if you sitting at this place, you remove this and this, you are getting this value, right? Which is what 16 is. Now, when you go to this particular place, you will remove this and this, you will get to this particular place, which is 15 is, right? So you eventually are multiplying 11 into 16, 11 times 16 plus 12 times of 15. So your formula basically is AD minus BC is coming from the same value actually, plus Cij, it will minus, because Cij is equals to minus 1 to the power I plus j, right? So this summation, whether you are using plus or minus here, it is all based on whatever value comes out to be there, right? So eventually your AD minus BC is the expansion of recursion which is happening at determined formula, right? So the determinant of A can be written down programmatically like this, or let's say you can also write it like A uh, 1j if you are expanding it across the first column, Aij C1j, right? For all j is equals to 1 to n. This is what the formula of determinant is. But just to simply understand, determinant can be expanded across any of those rows, even and any of these columns as well. But now that you have looked into determinant also gives you how much area or volume gets scaled while the transformation is happening. Okay. Now think of from the perspective, you learned about two different matrices, lower triangular today and upper triangular. We are going to have an extra class next week, which is the week of 31, wherein we'll complete lecture 4 and 5. The idea is that so that we get to only 6, 7, 8, which are easier to complete in the next three. Okay, so lower triangular matrices, if you look into, they will be of this form: 1, 2, 3. Let's say that it's a 3 cross 3 matrix. 3, 1, 4, 0, 0, 0. Now the peculiarity of this matrix, lower triangular or upper triangular matrix, is this: to find the determinant of these matrices, you just can multiply whatever is in the diagonal. So the determinant of this would be 1 into 1 into 4. That's all. Okay, and that's why these lower triangular and upper triangular matrices are very important. So if you take determinant of a lower triangular matrix, if you have to find that out, or determinant of an upper triangular matrix, it would be nothing but what lies in the diagonal element. Just take a product of them, you will get to the determinant. Why? Now think of from the transformation point of view, and I'll leave at that stage. You already looked into these matrices. They do some sort of transformation. That's what you see here. Sorry, not that's what you see here, right? And because of which the area, or let's say if this would have been a three-dimensional, I'll show it to you in the 3 dimension in the next class. This area or the volume would eventually change. This area is changing. This is called as the scaling of the area, right? The determinant is nothing but the scaling of the area. Now this area in the green color is what you see as the determinant value, right? So why do, and this is a thought I would want all of us to understand, why do we see the determinant of formula actually like this, product of the elements in diagonal? Okay, why do we have this type of formula for lower triangular or upper triangular matrices, and what is the connection of that with this is what we'll get to in the next class. But I want all of you to understand, look into, or think carefully what exactly it is. We'll meet in the next class, in the next lecture. I hope this has given you some idea about what LU or this transformation is. I have not told you about QR transformation. Reason for that is I told you about projections. Okay, projection of V on a vector V on U. So everything on QR is dependent on this. I just gave you an idea of projections today, which is what your QR decomposition, the I think third or fourth question on your assignment is asking for you to read about QR transformation, understand what exactly this is, and then implement. But what I'm telling you is QR transformation is all based on this part, or GS, whatever. It's the same thing. GS uses projection, and you can actually get to QR transformation using this. Read about QR transformation. Here, Q is the set of orthogonal vectors, or orthogonal vectors. Okay. So if you arrange them in a matrix, if you arrange vectors such that the first column, let's say the second column, the third column, let's say that there are three columns there. If all of these three columns are independent, C1, C2, C3, if they are independent from each other, then we call them as orthogonal matrix. This entire matrix is called as orthogonal matrix when column number C1, column number C2, column number C3, all of them are independent or they are not dependent on each other. Okay, that's what is orthogonal matrix. You read about R, what exactly is R, and the essence is you already know that to get to orthogonal vectors, you have a method in place, which is GS. And what I'll be doing is to just to help you understand and how to, because we are all discussing about all of these things, what I'll be doing is I will give you a simplified document to approach those questions, because I know that there is some ambiguity in part 2. So I'll share a document for you to understand what exactly is that those set of questions is asking, and a document explaining all of these things that we have learned: LU, LLT, which is the Cholesky, and QR. So I'll give you a document which will help you basically do the assignment. Good. Okay. Okay. Thanks, everyone. I think you can ask your questions in your chat, in the chat that we have. So don't worry about it. I'll get back to you. Sure, sure, sure. Okay. Thanks, everyone. Thanks. I'll share it today, Vivek. I'll share the document today. Don't worry about it. Today by tonight. Yeah, yeah. Let me open it up for folks who are here.
Hi, sir. Good morning.
Good morning. Good morning.
Just my questions are only related to the assignment, nothing else. First thing, just to quickly clarify what I understood to give answers for 1A. So I'll just put the screenshot of REF, RREF, and then I'll explain it using any small matrix. Like in words, when I write, I will use example from my own, a small 3x4 matrix. And then
Right.
for part B, pivot, non-pivot columns, and find a particular solution and the general solution. Now, particular solution we'll find from the RREF, we'll do back substitution and find the answer, correct?
Exactly right.
And we will replace the B matrix with 0 and find solution, the general solution. That's it.
That's right. That's right.
Perfect. And then the last is 6x9. So for C, I will not put any code snippet. I will only put the random 6x9 matrix that system
Matrix.
will generate
Mhm.
and just give the answers, screenshot
That's
of
right.
answers.
That's right.
Perfect, sir. Perfect. And then for the LU LLT part that you taught just now, we have to again do the coding part of it, and the same way, like 1A, 1B, we'll do that, correct?
Right. Exactly. That's the
Perfect, sir.
exact the
Perfect.
same thing. But
Perfect.
I'll
Great, sir.
I'll give
Thank
you the algorithmic way of thinking about LU and Cholesky and QR in that document, so that you have the hints of thinking
doing
how to
the
code
coding.
them. Right.
Mm,
Exactly. That's right. Okay.
perfect. Great, sir. Great. Thank you. Thank you, sir.
Okay.
Sir,
Yeah. Yeah.
just
Go ahead.
last. In the 1B, the equations we have to solve, so AX equal to 0 and X equal to B. Does that have to be coded or it has to be done handwritten?
It has to be coded. It has to be coded. 1A and 1B,
Okay.
both of them. You
X
can
equal
take
to
the
0 and
use
X
of
equal
L. You can take the use of LLM. That's what I'm asking. But you can actually get hints from it and then understand it if you are finding it difficult. But anyways, you have to code it. Apart from 1C, wherein you will be using already what you have coded to generate the output. 1A and 1B, you will have to code it. Even 2A, 2B, and 2C, I think all of them you will have to code all of them.
Okay, only 1C is something I have to do it on my own handwritten, right? No,
No,
sorry.
you don't
The
have
code, the
handwritten.
code
You will
generated.
use, yeah, exactly. You'll use the already generated code, put in the value of number of rows as 6 and number of columns as 9, generate a matrix, and then share the output.
Okay. And in 1A, 1B, I have to code it as well as I have to write through hand and then take a snapshot and create a PDF.
Right. That's right.
Okay. Same goes for second also, right?
Same goes for
Second
second
question.
also. That's right. Where
Thank
is
you
your
so much, sir.
assignment? Okay. Elon. Yeah, go ahead. Go ahead. Sure, has that problem.
Sir,
Yeah.
I'm audible. Sorry.
Yes, you are audible.
Yeah. My question is that, so for the second part, we follow the same steps as the first one, right? So we do form a random matrix, and then we follow LU and Cholesky, and we solve it manually as well as the code snippet, right?
That's right. That's right.
So it's not just the code snippet for the second part,
Yes,
because
yes,
that's a
that's
little
right.
confusing. Okay, yeah. And then for like even like for A, B, C, and D, we follow all four. We have to solve it. Sorry, other than D, I think A, B, and C, we have to
Yeah,
solve
A,
it
B, and
manually.
C will solve it. Exactly. That's right. So A is your LU, B is your Cholesky, and C is QR decomposition. You just read about QR decomposition because this is a reading exercise. If you see, they have asked you to read about QR decomposition of matrix and what exactly Q and R are, and then do these two parts.
Okay. Okay. And for D, we just have to, whatever the
Use
code
the
snippets we
yeah.
formed, we have to just solve it on the
Yes,
basis
yes,
of that.
exactly. Whatever you have generated for C, use that in part D and then solve it.
Okay. Okay. Thank you.
Sir, is the three decomposition document that you shared enough for the assignment 2?
I will the for question number 2,
Yeah.
I will be sharing a document to help you understand how to think programmatically about these three, along with some examples on each one of them. Okay, so it will help you understand what exactly it is and how to you essentially code them. So I'll not give you the entire code, but I'll give you the hints on how to exactly solve them, how to think from the program point of view. Okay.
Okay, so this is in addition to the 3 decomposition document that you shared.
Yes, yes, this is in addition to that.
Okay, okay, sure. Thank you, sir.
And I'll share it with today itself. Okay. Okay then. Thanks
So,
everyone. Thanks. Yeah, go ahead. Go ahead. Go ahead. Go ahead.
so sorry, just two quick questions. Now, obviously for generating the random values of the elements, we'll use the random function, right? The built-in
Right.
one.
Right.
And
Right.
second, so I'll use that. And second is, can we expect such programming questions in the exam?
No.
Perfect. Great. So thank you. That's a good news. Thank you.
So same question again. Like I'm new to this programming part, so I just want to understand. Like we need to put all the syntax and all the programming codes in our handwritten format here, or just
No, you can copy. Obviously it would be very difficult to write the syntax in handwritten. So what you can do is you can take a screenshot of it and show it to you. The screenshot of the code along with the output of the code that would do. And if you are new to it, I would recommend use Colab. All of you who are new to
yeah, that's what I am using. Yeah.
yeah, sure,
Okay.
right.
Thank you, sir. Thanks.
Okay.
Sir, one question.
Yeah.
Where we have to submit our assignments means via virtual lab or we have to upload it on Takshila?
You have to submit your assignment via on Takshila, not via virtual lab, on Takshila itself. Let me download this and share it.
Sir, so every question we have to code it, right? It's not like only one or two questions we have to code and remaining will be handwritten.
Yes, you will have to code, and not every question, but part question 1C and question 1D. They are all based on what you have coded in the previous parts. So
The
not every
pre
question
Achha,
needs.
okay,
Yeah.
got it. So question A, B, C will be coded and D will be execution for those three.
Right, right. So D is the execution of part C in question number 2, if you see, because C and D are QR decomposition questions. Okay. And whatever you take into as M cross N in part C is what you will be using in part D.
Okay, got it.
It's just that it is asking for linearly independent columns. You'll have to add one new criteria set that the columns are linearly independent. So those are the columns of matrix Q. But anyways, I will share you the document with you, which will help you understand that.
Okay.
Okay. Okay. Thanks, everyone. Thanks for joining.
Thank you, sir.
Let's meet next week. No permission. Which one? The solicitor permission. You should download it. It should ask. It should get to downloads. But anyways, I'll share it in the Teams and no problem. Stop sharing. Stop recording. Thanks, everyone. I'm going to drop. I'm just ending the meeting.